Good afternoon. I'm Professor Sever, and welcome to my video notebook series on linear algebra. Today we are reviewing notebook number 1 on linear equations and linear systems. Let's begin. As previously stated, in this notebook 1, we are introducing systems of linear equations. And as you might expect, we start with definitions. So a linear equation in the variables x1 through xn is any equation that can be written in the following form. Okay, and we'll look at some examples in a moment. So what we have is the coefficients are a1 through an. The variables are x1, x2, etc. up to xn. B is the constant of the linear equation, and of course the scalars or the coefficients may be real numbers, and later in the course we will see they'll allowed to be complex numbers as well. Now that's a linear equation. So what is a linear system? Well, simply a linear system is a collection of linear equations in the same variables. So let's look at initial examples of just equations. So we have A through G examples, and is the first equation a linear equation in x1 through x4? And the answer is yes. We can see it satisfies our definition. A1 is 6, A2 is -9, A3 is 0, and A4 is -4, and the B would be 16. What about this next example? Well, first we would note the variables aren't x1 through x4. The proposed variables would be x, y, z, and w. That's okay. We named them earlier with subscripts, but here we would presume the only variables present are x, y, z, and w. Is this a linear equation? The answer is yes. The fact that the coefficient of the first term is square root of 3 makes no difference. That is, in fact, a real number. In the third example, part C, I think we can see the answer is no. We have a product of two variables here. You cannot have that in a linear equation. So this one would not be linear in x1, x2, and x3. D would not be linear. It may look linear, and if you thought, well, let's take the square root of both sides, and you would get x1 minus 2x2 equal 4, well, you would be forgetting about the -4. So really this would produce a collection of equations, and that's not a single linear equation. Also, if you thought of it, if you multiplied this out, you would get x1 squared minus 4 x1 x2 plus 4x2 squared. And the x1 x2 term would be enough to indicate that it would not be linear, as in example C. Now what about E? Well, let's see. Is this linear in x1 and x2? Well, 0 times x1 should be 0. 0 times x2 should be 0. We would get 0 plus 0 equal 1. That doesn't seem to make sense. So is this linear? I'll leave it to you for a moment, and I hope you answered it. The answer is yes. This is, in fact, a linear equation. Now, in college algebra, these were excluded from being linear, but in this course, this certainly meets the definition of a linear equation in x1 and x2. Let's look at the next example, F. Yes, this is linear as well, similar to the logic of E, but of course 0 equals 0, so this one might be less troublesome for some students. And let's look at G. What about x1 over x2 equal 1? Can we just multiply both sides by x2 and get that x1 equal x2? And remember, in part B, in our mind, we were thinking about, well, we could subtract w from both sides and get a minus w, similar to how we had a minus x4 in this example, and have a constant of 0 playing the role of b. So would we have the same setup here? If we multiply both sides by x2, or would we suggest that this equation would give rise to x1 minus x2 equals 0? If you thought this answer would be yes, it does, then you would be thinking it would be linear. However, this is not linear. You cannot divide by x2 here, so this is not a linear equation. And you would, if you think about it, your x2 could not be 0. There's no restriction on the domains of these variables in a linear equation. What is a solution? A solution to a system is a solution to each equation comprising the system. It's predicated on the definition that we would be familiar with in terms of solutions to an equation. So a solution to an equation has the classical meaning Therefore, a solution to a linear system is a solution to each equation that comprises the system. So let's look at example A. Is 0, 2, 4 a solution to this linear equation? Then in the equation, in place of x1, we would put 0. In place of x2, we would put 2. In place of x3, we would put 4. And we would see, doing the arithmetic, that the ordered triple 0, 2, 4 is a solution to this equation. Is 1, 1, 2, the ordered triple 1, 1, 2, a solution to this equation? The answer is no. When you substitute these values in here, we see that it's not a solution to the equation. Let's look at example B. Is the ordered triple 1, 1, 2 a solution to this equation? The answer is yes. You plug in 1 minus 3 is negative 2, and 10 minus 2 is 8, so it is. So now, in part C, we're actually getting to this definition of a system. So here we have a system. It's a collection of two equations in the variables x1, x2, and x3. Is the ordered triple 1, 1, 2 a solution to this system? The answer is no. And if you will take note, these are the same two equations that we just discussed. So 1, 1, 2 is not a solution to the first equation. However, it is a solution to the second equation. But since it's not a solution to both, or all equations rather, in the system, it's not a solution to the system. In our next example, what about 0 minus 1, 1? Is it a solution to this system? So we would check, and I think we can see that plugging in, replacing these values of 0, minus 1, and 1 for x1, x2, and x3 respectively, we see that it is a solution to the first equation, and also it is a solution to the second equation. So the answer is yes. This ordered triple is a solution to this system. Okay, now, continuing our definitions, the set of all possible solutions is the solution set. That's consistent with the language that you would have seen in other courses. And finally, two linear systems are equivalent if they have the same solution set. So that's how we define equivalent systems, not that the equations are the same, but the solution sets are the same. This is our first theorem, the nature of solutions to a linear system. So if we had a linear system, there are only three possibilities. There is no solution to the system, there is exactly one solution to the system, or there are infinitely many solutions to the system. So what you can see is you can't have, for example, 5. You can't have exactly 5 solutions to a system. You either have none, 1, or it blows out to infinitely many. You have then infinitely many solutions. And now just some more language. A consistent system is one that has a solution, and a system that has no solution is said to be inconsistent. So let's look at our example that corresponds to these pages. And what do we see? Well, is this system consistent? The answer is yes. Let's recall, this is the same system we had on our last problem. It had a solution. 0 minus 1, 1 is a solution. Therefore, it's consistent. Now, just on that basis alone, all we can say is it's consistent. Equivalently, it's not inconsistent. We don't know yet whether it has only one. We have exhibited one solution, but we don't know whether it has more solutions. We could see later in the course, we'll be able to quickly see it's underdetermined. It has more variables than equations. It will have infinitely many solutions, but we can't actually say that now. Later in the course, in fact, in the next section, I believe we can make that claim. So let's consider some examples, and it's examples in two variables. Why? Because they're easy to graph. We'll look at graphical examples for each of these three cases. Let's look at the first example, the first graph. You'll see there is no solution because the two lines are parallel. Okay, and in the graphical solution, where the graphs would intersect, as you would see in the next example. So here we see two intersecting lines. These are two linear equations in x and y, or it's one linear system comprised of these two equations. And the point of intersection, since the point of intersection is on both graphs, we see the point of intersection graphically is playing the role of the solution to the linear system. So this is an example where you have exactly one solution, namely the point where the two lines cross. And you could have infinitely many solutions. Let's look at this next example. And of course, you only see one line. Well, the two lines are identical. Some people say the lines are coincident, they coincide, so one line actually is on top of the second line. I'll show you this in an animation. So when I superimpose the two equations, you see they land on top of each other, and hence you have infinitely many solutions. The two lines cross themselves at every single point that's on the line. And here's just a bonus graph, again, in two variables. Here's another example of a system of three equations that has exactly one solution. And just so you don't think that it has to do with parallelism, here's an example of three equations, again, in two variables that has no solution. There is no single point that is on all three lines. Thank you for watching part 1 of Notebook 1 in this notebook series. This video notebook lecture will continue in part 2. So we look forward to seeing you there. I hope you enjoyed part 1 of this notebook series. I'm Professor Sever. Thank you.